Welcome back, everybody. After this short introduction, I now want to discuss the first subject of this course, which is going to be about a work called Sparse IFDS that was published just a couple of years ago by the group of Jingling Zhu. And so we've already learned about IFDS in DECA 1. And this is basically about performance boosting, like the paper already says. It's a work situated in a more generic field called sparsification of static analysis. So there's a way in which you can make pretty much any flow-sensitive data flow analysis sparse. And I will be talking a little bit about this, but this is a particularly interesting work I find because it has some tricks that I will talk about when applying this to IFDS, which makes it actually particularly effective. Let's quickly recap traditional IFDS. So if you remember, IFDS is a distributive variant of the so-called functional approach. So the idea is to generate summary functions for individual procedures so that when you also that when the same procedure is called in different calling contexts and the static analysis needs to evaluate that callee procedure multiple times at different call sites, then you can ideally reuse these summaries, right? And in DECA 1, I used this example here, for instance, right, where we had this password that is being propagated here into foo. And we were wondering whether that can end up as an expression y here in this print statement. And if you remember, an important concept in IFDS was that we are creating these longer and longer path edges that you see here, right? And eventually, when a path edge spans the entire space from the beginning of the procedure to the end of the procedure, this becomes our summary function, right? And these intermediate path edges, they are created through individual flow functions, right? These are these grayish edges that you see here in the background. And we also discussed that because IFDS is a distributive approach, this allows us to regard every single data flow fact in isolation, right? Because by definition of this distributiveness, the data flow effects of each individual data flow fact can be computed independently of all the other facts. And that is an important property also when it comes to sparse IFDS, as you will be seeing in a few minutes. So the motivation of this sparse IFDS work is that in traditional IFDS, I mean, we already have a pretty effective and well-performing solution algorithm because of this distributiveness property. But still, even traditional IFDS does more work than is actually needed. And this can be seen by an example that the authors also use in their paper. So in the following, I will also be using a couple of slides that they actually provided to me. So let's take a look at this little example program here, right? So it's not doing all that much. It's assigning this source, so basically a taint to variable b. And that is being assigned, first of all, to an instance field, small a.f, but also then to a static field, capital A.h. And then here there are a couple of branches where this might be killed. And there's some code that doesn't really matter much to us. And then here we basically have the situation that A.f remains tainted because the taint is not killed. And A.h should be untainted because this is killed in both of these branches. Okay, so far so good. And now we can take a look at what IFDS would do in this example. If you remember, we are generating taints through such a gen edge, basically, right? That comes from this tautological zero fact and generates the fact B. And now in the next step, this would be propagated to B itself, of course, but then because of this assignment also to this access path A.f that we see here. And then this would progress, right? So this would be propagated further, but then in addition, B is also assigned to A.H, so we would also be generating this access path. And then this would go further and further, right? And so you can see A.H is actually being killed here at this statement, and then also down here at this statement, so that does not progress. But then the data flow for A.F that is actually proceeding right through both branches, and it's being kept alive, as you see here. The same is true for B and also for the zero fact. Now, what you can see here is there are a lot of intermediate steps, right? In particular, there's some not so trivial code here that doesn't actually concern A.F at all. It also doesn't concern B at all. But all these facts here, they're nonetheless evaluated with respect to that code, right? So there are flow function computations for these facts all over the place here, although this code here and also this irrelevant code here, right? It doesn't do anything to these facts here, right? So this code does act on A.H, but not really on anything else. Now that's where Sparse IFDS comes into play. And the idea behind Sparse IFDS is the following. So as generally the case in sparse program analysis, we now follow so-called def-use chains, so definition use chains. And yeah, a def-use chain, what is this? So it's basically simply a chain, so you could say a list of statements that link definitions to their corresponding uses. And here in Sparse IFDS, we have def-use chains that are specific with respect to a particular program variable, or in the general case, you should say an access path, right? And so what we see here, for instance, is at the beginning, the source taints B, right? So this is our initial access path. And so what Sparse IFDS will now do is it will create an initial def-use chain for this variable B, right? And that's what you see here on the right-hand side. So this is the def-use chain for B. Why is it constructed the way it is? Well, let's take a look at the code, right? So we are assigning to B, and then B is being used here on the right-hand side and there on the right-hand side, and never anywhere else again, right? So that means the statements at line 3 and 4, they are part of this def-use chain, but then nothing anymore, right? So that's why this is then terminated here by this exit node. And the idea behind sparsification in general, and also here in particular behind Sparse IFDS, is that you use these def-use chains as your primary object of analysis. So the data flow will now be propagated along these kinds of chains, no longer along the control flow graph. So there's a direct correspondence to the control flow graph, but in actuality, you're using these def-use chains only. But to make this complete, of course, you will need a number of these def-use chains, right? Because, of course, B is not the only expression that is being tainted here. So if we progress forward here, right? So you will see that, okay, the taint through this def-use chain is being carried forward to these two statements, right? And then we basically move to the next statement here. So we now have the statement A.F equals B. So that means A.F is actually being tainted here, right? And that means that we will now have also a definition use chain for A.F, like you see here on the right-hand side, right? So that's now the one for the next taint that is being generated, A.F. Now, again, we look at the control flow graph basically and create this def-use chain on the fly. And we will see that A.F, where is it used? It's actually only being used at the sink, right, at line 11. So that is the only other node that becomes part of this particular def-use chain. Then moving forward, we see that also we have A.H being assigned. So it's also a left-hand side expression that is being assigned the value of B. So we also need to create a definition use chain for a.h, right? And this now looks like this. So here we have, again, statement 4 in it, of course, but now also these two killing statements because they also refer to a.h, right? And then we have these uses down here, or there's actually a single use only of a.h here. So this, yeah, this is also being included in the graph. So you can say a definition use chain, it's basically a projection of the control flow graph with respect to a particular access path that you're looking at, right? And here we projected the control flow graph of this procedure onto the access path a.h, right? And that's exactly what we are seeing here. And now, like I said, in actuality, you're basically following these diffuse chains here. But what this means in terms of the control flow graph and also in terms of the exploded supergraph that we know from IFDS is what you see depicted here, right? So basically it means that because for the diffuse chain of B, for instance, only this node here is actually contained in the graph, and then basically nothing anymore, right? So the next was the exit statement, and basically means that while propagating B, we can actually safely skip all of these different computations here, okay? So, and no flow function evaluations in this part of the program here. Similarly for a.f, right? So that's also being evaluated all the way through here. So we can skip that code here. And for a.h, well, this statement is part of the diffuse chain, as you see here. This other one too, right? So here there will be some effects computed. In fact, this is being killed, right? So there is a flow function evaluation here and also there, which will then lead to these taints being killed. And yeah, like I said, so the idea is really that you create these diffuse chains on the fly. So whenever, so at the beginning, let's say you would start creating this diffuse chain because B is simply being assigned the source value, right? So that's the initial taint. So you create this diffuse chain for B. You then uncover that B is being assigned to these two expressions, to a.f and a.h. So you then create new diffuse chains for a.f and for a.h. Okay, and then you do this again, yeah, for everything that's needed, and then in the end you have your complete diffuse chains here. I think these, in fact, let me go back. I think these differ slightly from what I had on the slide. Yeah. So this is a graphic actually taken from the paper where they have a slightly extended example. So not to get you confused because these graphs look a little bit different. So if you take a look at the original paper, you will see that these are actually the particular graphs that they compute. But I hope you get the idea, right? So you iteratively create one graph after the other for all the expressions that are actually tainted, each one being a projection onto the respective access graph. And that's it, right? So then you're basically operating on these graphs only, and you can skip the regular computation on the control flow graph. And if you take a look at what the effect basically is, right, then you can see that if you have this non-sparse original IFDS propagation, then this propagates facts and every single fact to the next statement, right? So everything is propagated to the next statement unless it is killed, of course. And in sparse IFDS, you rather send facts directly to their next use statement, right? So for instance, here a.h, that occurs again here. So it's being propagated here, right? And a.f, which is being tainted here, that isn't used until down here, right? So that's why this is being propagated until this statement here, okay? And What's important is that this nonetheless computes equivalent analysis information, right? So after the whole analysis execution has terminated, you will find yourself having exactly the same analysis information at exactly the right statements, at exactly the same statements as you would have in IFDS. There's no loss of precision and recall, right? Of course, you will have to adapt your analysis machinery maybe slightly, right? So for instance, this particular value B here, this fact will never, in fact, have reached that particular statement that will never have been computed. So you need to tweak your analysis so that it simply gracefully returns the fact that B does not hold at the statement here, right? But this is easily done. That's just a matter of engineering the analysis engine correctly. And the key insight of this work is really that some flow functions, in particular in this IFDS style of propagation, there are fact-specific identity functions. What do the authors mean by this? Let's take a look at the original dense propagation again, right? Then maybe, for instance, we can pick out this particular case here, right? So here we have a situation where we are looking into a.f at this particular statement, but a.f is not at all relevant to the statement, right? We can definitely exclude that there's any effect on a.f. So that means that this particular statement here is associated with an identity function for that particular fact, right? So that's important. So it's a fact-specific identity function. It's not an identity function as a whole, because certainly that statement does have an effect, right? But it does not have an effect on that particular expression, on that access path. So for that fact, we have the identity function. And you can do the same here. Well, that's simply an expression being evaluated, so that is effect-free anyways. But also here, this statement has no effect on a.f, right? And now if you continue doing this, you will actually find that all of these here in this example, I mean, the example is well chosen, right? But nonetheless, all of these different functions here, they are fact-specific identity function. And that means that you can actually project them away, all of them, right? And so that's exactly what Sparse IFDS gives you, right? So it's recognizing these fact-specific identity functions by basically projecting them away when you are creating these diffuse chains, right? So they simply do not become a part of these diffuse chains in the first place. And that's why they are then implicitly excluded from this computation here. And again, right? So if you look at this whole flow function as one, right? So basically, you could also say in IDE we talked about environment transformers, right? So the transformer that takes all of the data flow facts from before the statement and transforms them into the data flow facts that are required after the statement. If you look at this as a whole, then this is not an identity function, not necessarily, right? But again, if we look at individual statements, such as, or individual facts, such as this one here, then we can have fact-specific identity functions, right? And that's exactly what this approach recognizes. Now, what's the workflow of Sparse IFDS? How was this actually constructed? You can see that it's constructed as this. So they actually implemented this in a tool called Sparse Droid. So it operates particularly on Android apps and implements an efficient taint analysis for Android apps. So as an input, you get an APK, so basically an Android app in bytecode format that is then being transformed into an interprocedural control flow graph. And then they actually did sparsification on 2 levels. I'll still be talking about this, but it's not sufficient to actually use taint analysis as such. You actually also need to have an alias analysis, like you see here. And the alias analysis that they built upon, that was actually also implemented using a particular variant of IFDS. And so they actually implemented the Sparse IFDS solver for both of these analyses, right? So for the taint analysis and for the alias analysis. That's why it's also depicted as such. But in both of these cases, they basically have this iterative approach where they create basically these sparse control flow graphs or value flow graphs, or you could also say diffuse chains, right? They create these graphs on the fly as they are needed, right? And they have a cache so that they are not ending up creating the same sparse control flow graph or the same access path and the same procedure multiple times, right? It's being cached here, and only if they have a cache miss, right? So if they find a graph not yet being present in the cache, then they're actually building it, and then they're caching it, and then they are returning it, okay? And so all these graphs are being created and evaluated on the fly. And the actual dense control flow graph is then not really used for evaluation by the analysis any longer, right? It's only being used to create these sparse control flow graphs, but then that's it. And in the end, yeah, so this is a big, indirect fixed point iteration. So the taint analysis may call the alias analysis, and that may actually also call the taint analysis. And at the end, both of these analyses will jointly have reached a fixed point. And then the analysis has terminated, and it will report any data leaks that have been found. And in the paper, you will find a bit more formal representation. So what you find here is actually a formalization of the IFDS implementation, or the IFDS algorithm, I should say. That's actually a denotation that's rather close to the original IFDS paper. And in particular, this function here is interesting. So that tells you how you are extending certain jump functions, certain path edges. So this is taking a path edge here that's starting at the procedure's starting point, SP, for a certain data flow fact D1, and it's going all the way to a target node N for a data flow fact D2. And then there's a case-by-case distinction depending on whether the current node that this is pointing to is a call site, whether it's actually an exit node, so an exit statement of a procedure, or whether it's a regular node. And you will now see that for call sites and also for regular nodes, this is doing something special. So that's basically in the case where normally in the original IFDS algorithm, you would actually be dipping into the already computed summary edges. So these are depicted by this symbol here. So whenever there would be normally summary edges being used, then they're actually checking whether they've already constructed such a sparse graph, and if not, then they are building it. And then once it has been constructed, then they are basically using this particular graph then for the actual propagation. So I won't explain this in much more detail here. In case you are interested in the details, I encourage you to take a look at the paper. It's freely available. So you're welcome to take a deeper look there. What I do still want to talk about is what is actually the impact on the runtime and memory consumption that this has. So does it actually work in short terms? And the authors, they had the following experimental setup. So they compared this, first of all, against the current state of the art in Android taint analysis, which is FlowDroid. That is a tool that was actually developed at my own lab a few years ago, and that I will still be talking about a bit more deeply later in this course. But FlowDroid is basically implementing a general taint analysis for Android apps, also on bytecode, similar to what I discussed here. And it's also using this indirect recursion between the taint analysis and alias analysis, like I already showed. The only difference is really that FlowDroid does not use sparse computation. It uses rather the traditional dense control flow graph. And Sparse IFDS now implemented this caching-based creation of the sparse control flow graphs that I presented. And it actually also used then multi-threading mechanism to actually do multi-threaded computations. But FlowDroid already has that as well. So both implementations actually use multiple threads to propagate the facts through the program. And then the authors used 34 apps from Fostroid, so that's free open source Android apps, and also 6 apps from Google Play. So these are closed source apps. And then they used the following platform. What's probably interesting to note is that they did use a lot of memory already, so 220 gigabytes. I don't think that any of you probably has that much at home, right? So that's the heap space that was given to the running Java virtual machine, so the one that was running the analysis. Nonetheless, they gave 5 hours time budget to the solver. So if that's not sufficient, then I don't know what will be, right? And they used 8 threads to propagate facts. Okay. Now, there are detailed results in the paper. Here I will only show you a summary. So they did get speed ups and sometimes significant speed ups, right? So in the worst case, it was a speed up of a factor of 1.1, so slight speed up. In the best case, it was drastic, right? And even on average, there was a factor 22 speed up. So that's still pretty substantial. And on average, Sparse finishes analyzing the apps that were tested within 18 minutes. So that's still a longish time, considering the apps. But you will see actually that it's a lot better than what was possible with the original FlowDroid. In particular, now if you look at these 3 example apps that they chose here on their slide, you will see that FlowDroid actually timed out on these apps. So after 5 hours, it was still not finished, despite the large amount of memory that was given to both tools. Whereas SparseDroid actually finished within a reasonable amount of time, right? So within a few minutes. Similarly, you can also see for memory consumption that there were not only these cases, but actually 6 in total where FlowDroid ran out of memory. And that actually did not happen for SparseDroid at all, as you can see here. In general, the memory consumption of SparseDroid was actually better than for FlowDroid, but in some cases it was not, right? So you can see here in particular, but also in these other blue circle cases, SparseDroid did actually use more memory. Now you can think about why can that happen? Well, they are creating these additional data structures, right? So they are creating these sparse value flow graphs. And of course, this only pays off if the data flow not already happens to be very sparse in the first place, right? And that is a property that's hard to determine upfront, right? So maybe one could do some additional heuristics first to see whether the sparsification is actually worthwhile or not. But then again, running such heuristics also takes time, right? So at some point, it's a trade-off, and you have to decide whether that's actually worth your while or not. And here they didn't implement any additional heuristics, so they create these sparse value for flow graphs always, right? And I think that's also totally okay. Otherwise, it would have complicated the comparison even more. But then you do see these artifacts here every now and then. But it's not dramatic, right? I mean, so if you have an increased consumption of 50 megabytes, oh no, it is actually gigabytes, right? 50 gigabytes opposed to 70. Okay, so that is actually substantial. Yeah, but nonetheless, so this may be an area that can still be improved, but over the existing state of the art, there's definitely some large improvement here, right? And yeah, so I think it would be interesting to look deeper into some of these apps, right? So I'm actually surprised that Floatroid was performing that badly on some of these apps. So they're probably already of substantial size. Looking at this chart, you might think that Floatroid is a horrible tool, um, but knowing a thing or two about it, I can tell you that it's actually still um, the baseline that many researchers take even today for their research. So it can certainly still be improved, like you see here, but it's not a terrible tool in general. So I'm not quite sure what was going on with these apps here in the first place. So some lessons learned from this. So sparsification in general. So there are other papers that use sparsification. So it's been a field of active research in the last 5 years or so, I would say. And sparsification in general essentially replaces the control flow graph with a so-called sparse value flow graph. Here in the paper, they call this a sparse control flow graph, but I actually think the term value flow graph is more appropriate because this graph that you also saw on the slides, to some extent, it's still encoding control flow, but in some cases, it's also missing control flow that is actually in the program. For instance, if you have an if then else branch that is totally irrelevant to a given data flow, then it will not occur in this graph. Hence, I think the term SCFG is actually a bit of a misnomer. Other papers use the term sparse value flow graph, and I think that's more appropriate. So in such an SVG, one usually omits nodes that represent statements which have no definitions and no uses at all, right? So in other papers, if you look at sparsifications, they will basically eliminate all these statements that have no relevance to any assignments whatsoever, that don't assign values. So that also means you then typically have one sparse value flow graph per procedure, period, right? And that means you can also then create one sparse value flow graph for the entire program by combining these individual per method value flow graphs. But that's not the case that you have here, because here the authors, they go further, because even at assignments, they identify individual fact-specific identity functions that can also be omitted, right? So here, the value flow graphs, they are more sparse, right? There's not one graph per procedure, but there's actually one graph per access path and procedure. So they have more graphs, but each individual graph is more sparse. And this can be done without any loss of precision, actually, because we are doing this on top of IFDS, right? So you couldn't do this for a non-distributive framework. You can only do it for a distributive one. So I'm pretty sure this could be lifted to IDE without any problem. So that would be a rather trivial extension, I think. But here they restricted themselves to IFDS. Yeah, because it's IFDS and in particular because it's distributive, you can do this per fact. And then you have these SVGs that are computed on the fly, like I showed you, and then they're being not just constructed, but also being evaluated, executed in parallel. And the authors here, they instantiated this particularly, this sparse IFDS for taint analysis. And you can think about whether that's actually a restriction or not, or whether it's actually generally applicable. Well, if you really look at bare IFDS, right? So no extension with IDE, so really IFDS only. And you think about what you can really sensibly do with IFDS, and IFDS as such is really actually rather restricted, right? So I find very few applications of IFDS that really go strictly beyond taint analysis. I mean, you can implement other analysis using IFDS, but then usually you don't really want this. We already discussed this in DECA 1. If you have any information, for instance, that is dependent on the context, you would rather want to put this onto your edge functions. And then you're already using IDE essentially. So, it makes sense, first of all, to instantiate this with a taint analysis. But nonetheless, this is a simple reduced setting because in one sense, it allows one to very easily identify which statements will have an effect on which values, right? So, and that's essential, right? So in the approach, you need to be able to identify what effects a flow function has on which values in the first place, right? So, for instance, you need to know that this is not an identity function for the access paths A.F, and B, right? And you can do this easily for taint analysis because you can just look at the statement, you know what the taint analysis does here, and you know that it has an effect only on these values, okay? But instead, you may consider some other type of analysis, for instance, a type state analysis, right? So an analysis that changes some internal state depending on, let's say, a certain API call, for instance, right? And so, for instance, type state analysis can be used to identify double free vulnerabilities in C and C++ programs. So normally, it's not a good idea to call free twice in a row on the same pointer, P, because that can lead to exploitable security vulnerabilities. So these are cases that you want to identify, right? But in order to know that you have a double free vulnerability, when you are looking at such a free statement here, you need to know through some internal state that the analysis is tracking that P has been freed already, right? So if you don't have that state, then this doesn't really tell you anything, right? And this is a simple example. You can have more complex type state properties, then this becomes even more clear. And if you were to model this in IFDS, then yeah, it would be less clear actually how to identify these fact-specific functions, right? Because whether or not this statement actually has an effect even on P, it actually depends on whether P was freed or not in the first place, right? So before the statement. So you might over-approximate in this case, but it might be hard to make this exact determination whether you have a fact-specific identity function here or not. Another important case is actually aliasing, right? So take another look at such a statement here. So here we have a situation where A.F is being assigned the value B, but now assume a situation in which a variable C aliases with A, okay? So they both point to the same object. Then this means that this statement not only can have an effect on A.F, but also on C.F, right? Because they are essentially the same. And that's then important, right? So it means that this statement is actually not having a fact-specific identity function for an expression C.F. So in particular, if you want to implement a strong update, actually, in this case, you might need to kill C.F, but even if not, for instance, if C.F was not tainted earlier, but B is actually carrying a taint, then here you also want to taint C.F, right? So even in this case, so that would be a weak update situation. Then also here you want to be able to generate this taint, right? And so I have to say, looking at the paper, it's not entirely clear how this is handled. So I assume this is handled because FlowDroid and therefore also SparseDroid uses some on-demand alias computation. So that means when they're actually evaluating such a situation in their sparse value flow graph, I think they're actually triggering then an alias computation on the fly that will inform them this way. That would actually make sense, right? Then you can even sparsify this alias computation, and then when you get your aliases returned, you can take them into account here. But it's something that you do need to take into account, right? So in this case, also identifying what is a fact-specific identity function and whatnot, it's not super trivial, right? So you need to take care of these aliases as well. Yeah, that's all I wanted to present for today. So just to summarize, we have briefly recapped IFDS, and we have seen this nice sparse extension of IFDS. And yeah, my personal opinion is it makes a lot of sense. Like the authors showed, it does save a lot of computation time. If you look deeper into the paper, they also make an argument that it basically can help increase the amount of parallelism that is done in your program or in your analysis computation, because basically you can easily create these SVGs on the fly and in parallel, and can also evaluate them in parallel. I do think that that also makes a lot of sense. That's a sensible argument. And so, yeah, if I were to implement a new state-of-the-art IFDS or maybe also IDE data flow solver in the future, I would certainly try to implement it this way. So I think that's definitely a step forward. Yeah, so I thank you for your attention, and we will be carrying on with other topics next week. I'll see you then.